So today we'll be looking at chemistry paper 2, right? Of the physics prelim in Gauteng. Okay, so this paper was written today. By today I mean the 26th of September, I believe. Yeah, right. Yeah, it is 26 today. Yeah. So we're going to be looking at question 9 first, right? So this is the last question of the paper, and it's obviously electrochemistry. And under electrochemistry, to be specific, this is electrolytic cell, right? So remember, electrochemistry is divided into two, right? In electrochem, right? We have the galvanic, right? I'll just say G here, and we have the electrolytic, right? So I'll just say elec, right? And they are divided into two, right? This is electrochemistry, right? And obviously under electrolytic, there are different processes, but to put it mildly, what happens is that how you'll identify that this is a galvanic is if you see a voltmeter, and I think a light bulb as well. And then here, if you see a power supply, a battery, whether they do this and then they write DC supply or they write power source, right? That's how you'll identify if it's in the electrolytic, right? But without further ado, right? Let's remove this guy here. Okay. Yeah, so without further ado, let's go. So now we can see something here. We see that this is a power supply, right? We see it by the negative and the positive terminal that we have here. And obviously the longer side is the positive and the shorter side is the negative, right? So before we even get to answering the question, let's see what's happening there. Okay. So they say the diagram below represents purification of copper or to pure copper, right? So this is called purification process, I think, of copper, right? Under electrolytic. And what happens is that we're going to take something, we're going to mine something somewhere, right? And that something has impure copper in it, right? And it also has pure copper in it. But what we want to do is we want to take this thing, right? And take out the percentage of copper that is pure, right? And extract it, right? And so what happens here, right? In an essence, is that when copper is purified, or when it is mined first, it comes with some impurities. What this means is that it comes with a mixture of other metals that are inside. So the metals that are inside that are not copper will be part of this alloy here. It's called an alloy or a sludge, I think, right? And yeah, this represents the impurities. So the impurities can be silver, your zinc, and all those other metals that are not copper, but that form the impure copper that we are trying to extract the pure copper from. So that's what's happening here. So what's happening here is that they tell us that this is the purification of copper. They also contain zinc, silver, platinum impurities, right? So these are the impurities. These are the other metals that are not copper, but they are found within that impure sample that was mined. Okay, so what happens here is that we have an anode and a cathode. But how do we identify which one is the anode and which one is the cathode? Because they change, whether it's galvanic or electrolytic, they change. So we can do this, right? We can just write here. So we said that galvanic, we turn chemical to electrical energy, right? That we have. And then electrolytic, let's just write the first 4 letters, elec, right? But because we don't take L's, let's remove this L, okay? What this means is that, right? So what this means is that in electrolytic, we convert electrical energy to chemical energy, right? So now what we want to do is that we're going to put the C under the C, right? You'll see what I mean now. Okay. So by C under the C, it means let's put a C here and we put another C here. So we're going to be moving from positive to negative. So first of all, you write GCE, which is galvanic, represents chemical to electrical, and then electrolysis, electrochemical cells. That one. Okay. So this one represents electrical energy to chemical energy. So we start from positive to negative, right? So what this means is that we put a positive here, and then we put a negative here. And then we put a positive here, and then we put a negative here. So we move from positive to negative, right? Just how current flows. But let's not forget that we don't only have a cathode, we also have an anode. So the anode will belong on the E. Okay? So this is what it basically means. So you put the C under the C, then you say positive, negative, and then obviously your A and your A, right? So what this means to us is that in a galvanic cell, the cathode is positive. In a electrochemical cell, is it electrochemical? Yeah, that one, right? The anode is positive and the cathode is negative, right? So this is how you can identify the signs. So here, it goes without saying that we are dealing with an electrolytic cell, right? So what that means to us is that our anode is positive, right? So now let's go to our anode here and label it, right? So this is our anode. The positive side is the anode. And what happens at the anode? It's oxidation. Right? Before we even go into the questions, let's see what is happening here. And then obviously that's the anode. Then we have the cathode here. Cathode. And what happens here is reduction. Right? So how you can remember it is red cat, if you want. Red cat. Right? This represents reduction, happens at the cathode, and then here we can remember it as an ox, if you want. Okay. So this is what's happening here in essence. So we are taking this copper, right, that is coming from the mining industry, and we are trying to take out the pure copper out of it. So now one thing we should understand, right, is that we always see at the sea. Hey man, what do I mean by this? Is that we always see at the sea, right? So we always see at the sea. So whatever that we want to see the pure copper, remember, right? So what that means to us, what that means is that we're going to see at sea. We are going to see what we want to see at the cathode. What this means is that definitely here, this is the pure copper. And this is the impure. So we always see what we want to see at the cathode, right? So even if we are electroplating a metal or a ring, we're always going to put that at the cathode because we want to see at the sea. Right, so that's just the way you can remember it. But there's, of course, ways in which we can go deeper into explaining, but it's okay. So yeah, it's fine. Let's move on. So now, we've done a few stuff there. So this is the graph that shows an initial relationship between the mass of copper deposited versus the time, right? So remember that we are taking copper, right, out of the impure, and we are depositing it we're taking copper out of the impure, right, and we're depositing it at the cathode. Remember, right? So we always want to see at the C. So what happens here is that this graph shows a directly proportional relationship. How we can see that is that, first of all, it starts at the origin and it's a straight line graph. So it's straight. It's straight, yeah. Okay, so what this calls for us to do now is to write down the energy conversion that takes place in the cell, right? So energy conversion, obviously, this is what? Electrical to chemical, right? So let's just do that fast. And then 9.2, right? At which electrode, A or B, will the pure copper be deposited? We just said we see at the C. So it's obviously at electrode B, because B is our cathode. We see at the C. So we want to see the pure at the C. So obviously it's B. So let's go to 9.3. 9.3 says, write down the half reaction that takes place at the anode. Okay? So remember, at the anode, what happens is that we are going to have oxidation. Okay? So they're asking us for the half reaction that takes place at the anode. So let's understand something here. Okay? We have copper electrodes. Both of them are copper. It's just that one is pure and the other is impure. So what actually happens here, right? Let's just look for a different color. Okay, so what happens, right, is that we're going to take out some of this guy and put it on that guy. So if we were to go deeper into this, we'll understand that the mass of this guy will decrease. The mass of the impure copper will decrease so that it can be fed onto that electrode there. So now they're asking us for the half reaction that happens at the anode. So one thing that we should understand, at the anode, obviously, oxidation happens. But let's see something. In this here we have an electrolyte. Electrolyte is an ionic solution that conducts electricity, okay? So we have copper sulfate. So we understand that copper, this is made of what? Cu2 plus. And if we just break this up, this is SO4 sulfate, 2 minus. So understanding that like attract and unlike repel. Like yes, like repel and unlike attract. I'm sorry about that. So this negative ion, right, will go toward the positive, will go toward the cathode, right? And obviously this positive ion will go towards the negative terminal, okay? So this is what happens. So if we're to talk about B, what would happen is that this copper, right, will be found at B, okay? And what that calls for is that it will be reduced because the reduction happens at that electrode. So here, if we're to talk about reaction B, it will be reduced. What that means that this Cu2 plus, right? So remember, reduction is gain, right? Reduction is gain. So we're going to add 2 electrons. We're going to gain 2 electrons and produce copper solid. And this is what we want to see. We want to see pure copper at the cathode. So that's why we'll reduce that there. And then the sulfate will move here, right? But this sulfate, it will not react. It will not react at that cathode. I mean, at the anode, right? There's a lot of science that goes into it, right? But what we need to understand in this case is that this is still pure. I mean, this is still copper. The only difference is that it's impure. So what will happen is that at the anode, we are going to have copper solid coming out of it. So we're going to have copper solid, and then this is going to be oxidized. So we're going to have Cu2 plus, right, plus 2 electrons, right? So now it's quite clear. You can see that something is happening here. Look at this. This is producing copper Cu2 plus, and then this Cu2 plus is going to go to the cathode and reduce to copper solid. So we are taking out from electrode A and putting into electrode B. But let's move on, right? So what's going to happen at the anode is that we're going to have this copper solid, right? We can even include the S there, okay? And then we are going to oxidize that, right, at the anode into Cu2 plus 2 electrons. So this is what's happening there. And then let's move on. 9.4, right? It says, how will the gradient of the graph be affected if, as the reaction is allowed to proceed until completion, write down increase, decrease, or remain the same? So let's go look at the graph. So this graph is a directly proportional graph. So they're telling us that this thing will be allowed to proceed until it's finished, until completion. So this thing will go straight forever. I don't think it'll ever go, otherwise. Okay. So just let me know what you think in the comments. I think it'll go straight until it completes, right? Because it's a directly proportional graph, and the mass of copper deposited increases with an increase in time. And remember, the electrolyte is also not changing. So the concentration of the electrolyte is not changing, because we are taking out, look at this. In electrode A, we are producing Cu2 plus, and that very Cu2 plus is going to reduce to Cu copper. So the electrolyte's concentration is still the same. So the rate of reduction is the same as the rate of oxidation at that. Okay, so I think it'll remain the same. Just let me know what you guys think in the comments, right? So let's just say remain the same. So let's move to 9.5. Then it says that refer to the relative strengths of the reducing agent. So it's important that we refer to reducing agents. We can't talk about it being an oxidizing agent. Even if it's correct, I don't think that you'll get the mark, because they want you to be specific about reducing agents. And then it says to explain why zinc will not be deposited at the cathode. Okay, so zinc is one of those impure metals that are found, right, within this, this alloy, this one here. Okay, that mixture of metals that are impure. Okay, so what's going to happen here, right, is that we are going to compare the reducing agents of why zinc will not be deposited at the cathode. So what did we say? We said what will be deposited at the cathode is copper. So now they're saying why copper, not zinc, in other words. So let's go to our table here. So now let's just go identify the things that we're looking for. So we're looking for copper and zinc. Okay, let's see. Hey guys, and there are a lot of coppers, ne? Please be careful. So we're going to be using this one. There are a lot of coppers, guys. Right, we're going to be using that copper there. And then let's go look for our Zn. Yes, this is the Zn we're going to be using. So they're asking us, why is the copper being deposited and not Zn, in other words? Okay, so now we need to refer to the strengths of reducing agents. So on our left and right of our table, we will see something. We will see that increasing, reducing ability, increasing oxidizing ability. We don't want that. We're looking at the increasing, reducing ability. So what this means to us is that as we go down the table, the reducing ability increases. And remember, reducing ability, it's the same thing as the reducing agent. Okay, so remember, reducing agent is the one that is going to be oxidized. Okay, but it's fine. So now we can see that zinc is at the bottom. So it means that zinc has a stronger reducing ability. So we can just write that down. Okay, we can just say Zn, stronger reducing ability. Right, then Cu, right? It is important, guys, that you don't write Zn2 plus here. We don't write Zn2 plus. It's important that we don't write that, and that we write Zn straight, because we understand that something that has a reducing ability is something that is like a reducing agent, and the reducing agent can only be oxidized. So we can't, wait a second. Yes, right? So we need to write down Zn, okay? We can't write down Zn2 plus, because Zn is the one that is going to be oxidized to that, right? This can't be oxidized. It's already oxidized already, right? So, yeah. So that's what we have there. So it's important to write what's on the right-hand side when we're talking about the reducing ability. So, okay. Let's resume. So Zn has a stronger reducing ability than, yeah, okay? So what this means to us is that Zn, right, since it has a stronger reducing ability, it will be oxidized, right? So if Zn will be oxidized, it means that Cu is the one that is going to be reduced. Not Cu, Cu2 plus is going to be reduced, okay? And remember, what happens at the cathode? Reduction, not oxidation. Reduction happens at the thing. That's why this one is the chosen one, and not Zn. Okay, so I think that's the remarks there. Let's try and move on, and then, right. So the next thing, the next question rather, it says, when the current flows for 30 minutes, 15 grams of copper was deposited at one of the electrodes. So, okay, number of moles. So here they're not asking about current. Hey, sometimes they ask about current, and you need to know what to do. Okay, but they're not asking for current now, so it's fine. So what they're saying to us is that calculate the number of moles of copper deposited. So they've given us the mass. Okay, so they want the number of moles. Okay, so that's the number of moles is equals to m over m. Right, remember the top one is the mass in grams, and the bottom one is the molar mass. So the mass in grams was 15. Okay, all over the molar mass. The molar mass of copper, I have my periodic table somewhere. Let's just go use it here, this one. So we're looking for copper. Hey, they even use it as an example. So here it is. So that's 63,5. 63,5. And then I believe that this is 0,24, rounded off to 2 decimal places, moles, okay? So that's what is going to be deposited. So now it says that determine the number of moles of electrons that flows through the circuit while the 15 grams of copper is deposited, okay? The number of moles that flows through the circuit, okay? So let's understand something. We have this guy here, Cu, 2 plus 2 electrons. Rather, let's do this. Cu, right? Cu 2 plus, okay, plus 2 electrons, right? So remember, whatever is going to be deposited is going to be coming from the anode, okay? So the half reaction of what is happening at the anode was this one. This is the one that we wrote. So this is the solid, right? This solid is going to reduce into its aqueous form and 2 electrons. Yeah, I forgot the negative there, okay? So this copper is going to be reduced. I mean, it's going to be oxidized. But they are asking for the number of moles of electrons that flows through the circuit while it is being deposited. So it's going to be deposited from, it's going to come from the impure. So that's why we have where the impure was the anode. So this is the reaction that we're going to be using. So we can see that we have the number of moles of this guy. We've got check. Okay, but they want the number of moles of electrons. So these are the electrons here. So now let's understand something. This is normal stoichiometry, okay? It's just that they putting electrons here. So we just have to still be looking out for the molar ratio and all the other stuff. So now what we can see here is that, oh, the number of moles of Cu, right, compared to the number of moles of electrons, it's 1:2 ratio, okay? And we have this guy, this is 0.24 guy. And then this is what? N. We don't know that. So we just do cross multiplication, and we can see that the number of moles that will be, of electrons that will flow is 0.48 moles of electrons. And then, yeah, we are done with this question. So I hope you maybe grabbed something from the explanations, and yeah, so yeah, so just let me know in the comments what you think, especially about this question 9.4, right? Increase, decrease, or remain the same. And then yeah, we'll catch up.